So everything is on this link. Are we all on that Google Doc? Then I will try to log into the server again from scratch. There's some weird stuff happening with respect to the path. So I want to start cleanly. So I'm at the same page as you are. Okay. Before I start, just a quick introduction. This tutorial that we're going to do today is much more low-key, low-level than the tutorials you heard yesterday, which were kind of getting the entire pipeline. Here I'm focusing on one tiny part, namely to get from nifty files, any nifty files you want, to a layer profile. And this is a tutorial that I've given already upon the request from Sean, so he deserves credit. I want to thank Brian Hanna for helping with the setup of the scanner. I want to thank Daniel Glenn for helping me in explaining how to read and write nifties in C++ and the LAYNII program that we're going to use later. And we probably will not get to Shri's part with respect to alignment, but I want to thank Farouk with respect to some discussions of the number of layers. So this is a very personal description of how I do layering, or how one can do layering. I don't claim that it's the best one. I use it more as out of desperation because I'm not skilled enough to use FreeSurfer or CBS tools at accuracy level that I would like to have. And that's why I do it my own way. Also because CBS or FreeSurfer or any kind of vertex-based analysis toolbox usually requires to have whole brain coverage, to have closed surfaces with nice topography, and this is challenging, or maybe not very efficient. If you have a specific hypothesis about one brain area, then you might want to optimize your acquisition on the one brain area, and you don't have the entire brain. So I developed this to work on partial brain data. Also, with respect to what Jonathan said yesterday, layer fMRI is too easy. You can easily do it with any kind of resolution. You just analyze your data across depth. And the goal of today is to show you how easy it actually is. There's no magic happening. The things that we're going to need for this tutorial is to install LAYNII. Therefore, we need a C++ compiler. It's advised to have the GNU Scientific libraries too, which turn out to be a problem right now if they're on a different location. I figured that if you don't have it, we can still use it. The programs that we want to have without GNU Scientific libraries, but I will talk about that later. Also, we will need some tools to view images, so we will need FSLView or AFNI or ITK-snap or whatever tool you choose. I will use some basic AFNI commands also to extract the signals, and we need any data, obviously. I would like to use some V1 data that I acquired recently with the help of Sean at NIH. There are also some M1 data you can download here. They are on the server right at this path, and we will go to that. And you can also download them from OpenNeuro if you want to go through these steps later at home. Also, if you want to go through everything later at home, there's a blog post where I kind of go through the entire analysis in an M1 example. I talk about the number of layers, the grid resampling, upscaling, and so on. You can follow this blog post if you want. There's also a YouTube tutorial where I not only talk about the layering, but I talk specifically about layering with respect to VASO. So here you see this is actually a 33-minute tutorial where at the beginning I talk about VASO, how to do VASO analysis, and then later also how to do layering analysis, which is almost identical to the thing that we will do right now. So there are manuals there, and by the way, here I also have some background. The schedule changed a bit since yesterday, therefore what we go through today might be slightly different than what you find on the destination of those links. I think everything you need to have is on that Google Docs now. On this part of the Google Docs, these are just some paths that need to be set that we might not need necessarily. If you have FSLView and AFNI installed on your local machine, then you don't even need to go to the server. In fact, it turned out earlier that the server can have quite some delays, especially for the graphical interfaces. If you want to install LAYNII, I will show you quickly how you can do that. For example, here now on my local machine, if I go to any server, mkdir install LAYNII. So this is now a new folder, so let's go in that, install. You basically just copy this command. You clone the source code from LAYNII, so you download it. This might take a few seconds. It's, I think, 100 megabytes because there's some example data included. As soon as this is downloaded, now you can basically go to that folder, LAYNII, and there's all the source code. You can compile it with make all. The screen is big enough for you, right?
Something happened to the access to the layerification in the Google Doc.
You cannot access it?
Oh, it's a uppercase.
Uppercase L.
Yeah.
Uppercase L. That's right. Layerification is uppercase L.
It has to be an uppercase.
Okay.
Yeah.
This is correct, right?
Yeah, that works.
Okay,
That
okay,
works.
perfect. So now we compiled it. One important thing is that it depends on GSL. It turns out that this is a harder obstacle than I thought of, so I might get rid of it in the future. If you don't have GNU Scientific libraries, you can install it on Unix with sudo apt-get install libgsl 10-def, or on Mac with brew install GSL. I hope it works. I'm not 100% sure it always does. Or we have one example right now where it, for some reason, did not work. Okay, this is if you want to do it on your local machine. Let's do it on the server now, so we are all on the same page. So on the server, I'm now in my home directory. I think, yes. So my home directory is almost empty, so we need to get some example data. All the commands that I'm going to use are on the Google Docs, so let's copy the example data from the shared folder to our respective home directories with copy paste -r this folder here, and this should happen really fast. So now we have this folder in our home directory, which would be the v1_layering example. So let's go into that one, v1_layering example, and there you see we have the following data. We have 3 nifty files. We have a bold activation map, a mean time course, like a mean image from the time course, a mean vaso image, and a vaso activation map. And for some reason, we have another subfolder in here that makes me confused. Anyway, let's ignore that for a second. We have another subfolder for scaled images here. So does everybody have the nifty data in their local directory? Do you need like maybe 1 more minute? Yeah. Okay, let's give it 1 minute. Does anybody need help? Then just let me know.
I really can't see.
You can't see. Wait, then.
Can you increase
I will try.
Yeah.
Okay. So the magic thing that I did so far is copy the data from this path to the local home directory. And then I moved into the folder of v1_layering example. Are we all on the same page now? Then maybe we can take a look at those data. I would prefer to look at it with FSLView. In order to make FSLView work, we need the following paths. You can copy paste this stuff, and then we execute FSLView and look at all the nifty images within that folder. and this takes a while to load. So there we have our images. This is a slab acquisition of 0.54 times 0.54 times 0.53 millimeters. The matrix size in plane is rather big, and it's 26 slices. So it's a slab acquisition. I should give full credit here to Rüdiger Stirnberg from Bonn, whose readout was used here. It's a segmented 3D API, and the data were acquired with Sean at NIH this September. In order to make it better visible, and we don't need these kind of sagittal and coronal views, you can use Control 1 to only view 1. You can also go to Window and Single View to see it bigger. And then we can browse through it a bit more effectively. So right now this looks like noise mostly because the automatic scaling is kind of super weird. So this would be the vaso activation map. Let's scale this maybe from 2 to 6. Maybe that works. And let's make it yellow. And the same thing for the bolt. Let's make it yellow. And we choose a lower and upper threshold maybe from 4 to 10, which would be % in this case. The background image is just a mean vaso. So this is
Wow.
this is segmented API, and vaso has this nice feature that it has an inversion pulse, so it gives us some idea where we are in anatomical space too. And you can, like, we have 26 slices, so we can kind of scroll through it. And these data were acquired in a session with a flickering checkerboard, 30 seconds on off, and this is an average, I think, of 4 runs. All right. Does everybody have the data and maybe had a chance to open FSLView? Should I wait 60 seconds? Okay.
I'm trying to download the data set, and it says it needs, you have to give me access. I tried to go to the link from the page.
Oh, wow. Can you do a request access?
I did.
Wait, if you, so you want to download it from Google
From the link that you had there. The V1 layering data link right there. Sorry,
there.
See there.
This one?
Yeah.
V1 layering. So let's go to Firefox where I'm not logged in. Request. Oh wow.
Yeah.
Okay. Sorry about that. I will fix that.
Unless, the open neural data set is kind of
Yeah, then you need to download it with OpenNeuro. This takes a second. So we want layering, share. I have a shareable link. This is stupid.
There is a shareable link?
Layering example. How do I share it retrospectively?
You just make it.
Like, I'm a bit scared that if I do share now, get shareable link, then this might be a different one. Done. So let's try it again. Yes, this works. Suspicious. Yeah, okay, that's all right. So you can download the data there now.
So
Sorry about that. So now if you click,
now it's a shareable link?
I think it should be. Let's click on it. Now it should work.
After I type the FSLView, it says missing header image file.
You have to tell FSLView to use for empty files.
What's the command you use to execute FSLView? I think as soon as you
Maybe I should check if it's Yeah.
Don't use it.
Sorry.
Yeah, we use it for
Okay, are we all on the same page now? Okay. So these are the data. You can zoom in with the right mouse button. For example, back here, we care about the visual cortex. Right now, I'm on page, on slide 7, 6, whatever you like. Maybe, I don't know, but if you really want to see it, you might be able to see that there's a darker band following the cortical ribbon. This might be indicative of the tree of Gennari. Like we have very dark is CSF, then we have a few bright voxels, might be the less myelinated 2-3. We have darker voxels, and then white matter.
What's the black?
The background?
Yeah, what's that?
That's just because it's masked. Like if Vaso is inherently a division, so I'm dividing the null image with the not null image, similar like in ASL. And if I'm dividing by 0, then things get weird. That's why I remove anything that's above, I think, value of 5. Yeah, that's why it's black. So for bold, as always, you have a lot of significant voxels. It looks nice, or as nice as relatively speaking, I guess. We have large veins here for Vaso. It's similar. We have less significant voxels. It's not as sensitive, but you might think of it in a way that it's more sensitive to the voxels that we want to have. We have a reduced false positive rate in the superficial layer. It follows the cortical ribbon maybe more clearly as we follow through the slices, especially when the cortex is kind of very narrow here, where in bold you might not be able to separate that easily, where it's a big blob. And this is the reason why I like Vaso.
So what range do you have for Vaso?
This is beta values between 2% and 6%. In bold I have between 4% and 10%. Percent, yes. It is a very strong task, flickering checkerboard. So we want to do layers, and we can do layers with LAYNII. And for layer depth estimations, we of course need to know where gray matter starts and where it ends. And you can get these kind of borderlines from many different ways. For example, Alessio yesterday showed very innovative ways on how to get these borderlines. FreeSurfer might give you that if you know how to use it properly and are happy with the accuracy. Right now, for the sake of being fast, I want to do it manually, because then I know what I'm doing, and I believe that manually is always the most accurate, at least if you do it right. So to get these kind of borderlines, we can make a new mask. In FSLView, you click on File, Create Mask, or Control-C. In FSLIs, this is slightly different. So now we have a new kind of copy nifty image, which has the same dimensions. And we can use that to draw our eyes, for example, with this little pencil over there. And the default is that this pencil draws with a value of 1 and size of 1. So let's just draw a little borderline between gray matter and CSF.
Why my pencil button is disabled?
Oh, you have to create a mask. You have to say that you're creating a mask.
Because
Under
this
file.
one is locked.
So you under
I'm usually conservative here and try to not really draw the borderline between gray matter and CSF, but kind of more on the CSF side. I want to be more inclusive than exclusive. So I draw the borderlines between gray matter and CSF with 1s, and then I draw the borderlines between gray matter and white matter with 2s. For example, following here, I'm more on the white matter side on purpose, following the calcrine here. Maybe there, and then everything else that is gray matter, I want to fill it with 3. So I close the edges with 3, and then can use the bucket symbol, which would be right over there, and just fill it with 3s. Oh, this is with 1s. Go back. Where's my undo button? Here. I want to fill it with 3s. And right now, to be fast, I just do it in one slice only. If you want to do it properly, and if you want to have more voxels, which always helps with respect to SNR, I would advise to do this in 3D completely, not only a single slice. So this is kind of the borderline that we have now. And I heard from the earlier session that there is quite a lag sometimes when you draw, like because it's on the server. So again, I draw with 1s between gray matter and CSF. I draw with 2s between gray matter and white matter, and then I fill everything up with 3s. Masaki, do you need help?
Yeah.
Or you- Now you can just go to like change this to 3 and then just close it up on both sides. And then you can use the bucket, so it is here, and then fill it up with 3s. Okay, so you can use the undo button, and this means that you have a hole somewhere. And 3 is the hole. You might need to go back to the pencil.
Power of this is a can I think Renzo's way of how you can change build upon manually interpolation allows you to do it and now researcher is this one. Shouldn't have. It's close, right?
Try something?
No. Yeah, right. So, for example, Cheryl she feels
This works.
nothing is good enough. And let's just try and see how far we get and collect some more subjects to construct and hold my shit good enough and see what comes out. And there's also, for example, too, if we're doing this might be for every single subject, every single slide.
You can always use the eraser to draw it again.
So,
Probably,
yeah, right.
but this is alright. This should be not a problem.
So free surfer.
Ah, you know what? You chose different masks. This is a different file. It was never closed.
Okay.
So now we can redo it. So now you just need to draw the ones,
Right.
and then we can do it. Yeah. It was never closed. Yeah.
Okay. This kind of
Oh, you have the whole
region of
thing.
interest and
I
theory.
just do the
Yeah.
give it this hand, move it just
Oh, right. That's the way.
And now you
Oh,
can
yeah.
maybe draw it.
You see that? This one? No, this one.
Oh, yeah.
But then I had
Have to be continuous.
It has to be continuous, then you can fill it up later.
Okay.
Much better.
Okay.
So I will quickly
Basically,
erase.
that's what
Yeah.
Cheryl's trying to compile a list of things
In Windows, you can just double click.
And obviously every tool does it differently, like FSLView
Yeah,
does
yeah.
it slightly differently. I think ITK Snap does it quite effectively also.
So it should be different ones, like inner and outer layer.
Yes, the inner, like the gray matter CSF border
yeah.
should be once, the gray matter white matter border should be twos, and then
okay.
you can fill everything up with threes over there. Like that. And then with the bucket, you can fill it with so three. Like that.
Thank you.
Exactly. Yeah, that's right.
Mm.
This looks slightly different than just an hour ago. Let's not necessarily.
Are we all there now?
this one.
Okay.
Or
Okay. Then we want to save that. And this is a bit annoying because the server is set up in a weird way that it cannot really save it as we want it to. So let's save that as rim.nifty.
Oh, this one. Mean Basil. Mean Basil, so okay. Yeah.
So let's save that. And even though we call it rim.nifty, it saves it as rim.nifty.gset, which is unfortunate. But we can use a quick AFNI command to convert it back to nifty. In order to make AFNI work,
So you want to convert it to nifty because your LAYNII tools
can only work with nifty. Yeah. I used the, sorry?
I think the nifty C++ header should be reasonably underpinned. Right?
It should be, yeah. I never worried about that because I never had these weird issues. I didn't test it, and that's why I couldn't use it
I think
now.
what I
Yes,
wrote
you have
software,
to
in
Control
C++
C
with the
in order to
same
make a
library,
code.
I checked out your
Control C.
code,
Mhm.
And
and
then
it seems
copy
like
should be
it's
made.
reasonably possible
No.
with minor changes.
It should be absolutely straightforwardly
Anyway,
possible.
Sorry, please go on. Let me know.
Right, so in order to make AFNI work, we need to set a path
Then use it and then you can check it.
like this. Now AFNI should work. And then we can, in the next step, copy the rim.nifty.gset into rim.nifty. ls. And now we should have a file rim.nifty. Do you need help?
Yeah.
As
opposed to.
Let's try it real quick with control 1. Okay, never mind.
Yeah, control 1 didn't work.
And this is on the server now?
I didn't do it manually. Well, that's because I'm too late. What I, so in my particular case, we did it
Fill it up with 3
right.
rim.nifty. And now you should have it.
So then here what you do
Something
is
like
here.
that. Well, first you have to run a separate scan.
This is on your local machine.
No,
No,
so
it's on the
here,
server.
So what you want to do is
Okay.
So
now you can do
the
convert it to nifty by setting this the AFNI path, so AFNI works, and then you can use the 3D copy command as AFNI does it. Okay, now that most people have the rim.nifty file, we can use that to calculate layers. And the way how I do this is in LAYNII. In order to make LAYNII work, we set the path to LAYNII. And then there's the command ln_grow layers. If you type this in without any arguments, you see what it expects. It expects a rim file, and then you can specify a lot of different things. Let's not worry about them for now. Let's just see if we can execute it. Layers minus rim, and then we have the rim file rim.nifty. If we execute that, then it should do the algorithm, and it's a growing algorithm from white matter from CSF, and then it corrects for some Pythagoras errors.
Does that work?
No.
Okay. You cannot open the laptop. You cannot copy it.
Yeah.
The reason is
Sorry.
Yeah, don't worry. Don't worry. Yeah. Sorry? Yeah, that's a debugging thing. It doesn't crash until here. Sorry about that. It's still in there. I'm not sure why. Okay. So now we can. We should have a file that's called layers.nifty. So now we can look at that. in FSLView by add and look at layers.nifty. And here we have, like within the mask that we drew, we have every voxel now has a value, and the value refers to the cortical depth. This might be better visible when we look at it in a different color scheme. Maybe this one is nice, or I'm not sure which one is nice. They all look weird. This one looks nice. So we have now per default 20 layers. If we don't specify it, we can, for example, try the same thing with less layers, minus n6 or so. Now we have only 6 layers. Add the layers. And then obviously it looks slightly different. So here we have 6 layers, 20 layers, and so on.
So when you have 3D
Mhm.
data,
Right.
and you label 3D, today you label 2D,
Right.
does it compute in 3D? Meaning, does it take into account curvature?
Absolutely, sure, yeah. It must be 3D, yeah.
Right. So
Right.
you're doing like, you have something, like you have at any point you have a line which is orthogonal to the cortical surface.
Right, it uses minimum distances. I can show you what it does. So on the, there's a link in the Google Docs right down there where I explain the principle. So I'm basically, like, we draw the white matter gray matter boundary, and then it basically grows. It's a growing algorithm, so it grows and grows and grows until it stops at a CSF. This growing algorithm, however, is done in voxel space, step by step, and if you go one step to the right and one step up, it's 2 steps, even though the distance is only square root of 2. And in order to correct for that, in the next step of the algorithm, I blur this out, so so we don't have these edges and directions only rectangular, but also in any directions. In the next step, I kind of extend this in neighboring columns. So like every voxel gets the same value as the neighbor. And this in the Foley cortex, this can look weird because, for example, this voxel has all these voxels in green have the nearest neighbor to that one. So in the next step, I correct for that and make it more, like, make the individual layers, the columns or layers connected. The algorithm is the same if you do it in column space or in layer space. And in the next step, I basically just rescale it. So if you want to have one voxel as one layer, or if you choose the number of layers however you like, you just rescale it. With respect to the number of layers, the people have opinions. Right, I think it's advantageous to have many more layers than you have the resolution for, because then your binning is the smallest, and you don't have a lot of partial voluming. People tend to think that we should avoid numbers of layers that match the number of cytoarchitectonically defined cortical layers. So don't use 6 like Brodmann did, don't use 8 like Miner did, don't use 5 like Bolton did, don't use 9 like, it's arbitrary, right? If those guys were allowed to define the numbers of layers, why shouldn't we? It's right. So I use anything that I like because there's no standard, right? Why do I think we should use more than less layers is explained on this blog post that's also linked on the Google Docs. So when, for example, you have very thin layers, then you pool signal from all the voxels that touch this thin layer. If you have thicker layers, then obviously the range of the depth values that you pool signal from is larger. So this voxel also contributes to the middle layer, and obviously that results in partial voluming of different cortical depths. So for example, here we have a toy example of 2 stripes in a motor cortex. If I use very thin layers, the middle layer is not affected from the 2 stripes. If I use less layers, like only 5, then we have more partial voluming. It's like in any histogram analysis, you want to have small, thin bins. If you make them too thin, then you run into noise problems. For example, here, if we use 5 layers, 20 layers, or 100 layers, so if we use 100 layers, then you see that the voxels or that the points in the layers are not connected anymore, which can be a problem, especially in the animation up here. I hope it. Sorry. So here I use my double stripe example from the motor cortex to just play around with different numbers of layers. For 2 layers, you obviously don't see a double peak. 3, 5. At 5, you start to see it. At 10, we have more nicely separable 2 peaks. I think in this example, I have maybe 4 to 6 independent voxels across cortical depth. But still, the data look better if I reconstruct them as 10 layers, because then I reduce this relative partial volume. If I have 100 layers, you start to see that it kind of starts to become wiggly. And this refers to what Jonathan yesterday said, that you are kind of rank deficient. Right. Yeah.
So after the scroll, how to open which file?
If you still have the FSLView open, you can go to File and then Add. And then you should have a layers nifty file, this one. Yeah. Right. That's your home file.
So my FSLView just froze. Okay.
Sorry. Okay.
How many layers were just scrolled?
The default is 20 if you don't specify it. We had this discussion earlier. I think the most elegant or the least user-based way of doing things is to use the number of layers as number of voxels. Like, don't bin them all together, but look at the position of the voxel centroid and then plot the value of the voxel as a function of the position of the centroid. Obviously, then you don't have a continuous measure. But usually in many other statistical tests, you don't have that either, right? In fMRI time series, you sometimes censor individual time frames where you have a lot of motion, throw it out. So there are statistical ways to deal with that, like to just have a non-continuous fashion and plot it like Ravi Menon did in a kind of point plot like that. And then, Tim has ideas on how to solve that. It might not be a problem for layer-dependent fMRI. Like I know in particle physics, where I graduated, they have the same, like to find the Higgs boson, the same kind of plots, and then they do statistical tests on those. Is it a peak? Is it not a peak? Do you see something? I'm sure there's are solutions for that. We have these layers, and now we can try to extract the functional signal from that. Maybe I redo my analysis real quick, not with 6 layers, but with the default of 20. So we are on the same page with everybody. So you saw that we have these 20 different layers, and now we just want to extract the signal within these layers separately. And within the folder that we have, there's a script that's called afni_layerme. So when we just look what this does, this is as simple as it gets. Afni command, the command is called 3D ROI stats. So what it basically does is it asks for a mask, which is the layer file, and then in each value of that mask, it calculates the mean and writes it into that file. That's it. Nothing more to it. You could even do this with a calculator manually or with MATLAB or however you like. I do a bit more here. I not only want to know the mean, I want to also know the standard deviation and the number of voxels in each layer. The last line here is just transposing it, because Afni writes it as different values within one line. I wanted it columns, so I transpose it. So let's run this and look at Afni. Sorry, there's something weird. Afni layer me, and we give it the file that we want to have, like for example the bold activity, and hit enter. So now it extracts the values of each file and plots it right there. So here we have too many layers, I think. So what these 3 lines give us is the top line is the number of voxels per layer. And we have this bias that there are slightly more voxels in the deeper layers compared to the superficial ones. And this is just geometry, that when you have a concave like when you have a sulcus, you just have more voxels in the deeper layers compared to the superficial ones. The second line is the standard deviation, which is very characteristic for bold, that it's kind of flat within gray matter, and then we have this kind of L shape that towards CSF it kind of really shoots up. This is mostly physiological noise of the large PL veins at the superficial layers. The bottom row is the mean value of the bold signal change in each layer. And you see it's a linear trend. The superficial layers have a larger bold signal change than the deeper ones. This little zigzag pattern is an artifact that we have only like 3 to 5 voxels across cortical depth, but we actually extract 20 layers. So we actually might have overdone it here. If we do the layering with maybe 10 layers and do this again, then it might look smoother without these biases. And it's still kind of zigzag, but not so much anymore. Later, we will go through a more elegant way of first upsampling the data and then calculating the layers in a more smooth fashion. This is just to show you the principle, how it works. So this is the bold. Let's see how the vaso looks. Yes?
I think I don't have the API environment set up. Which
Do you have the Google Docs? If you scroll up a bit, the other way, the direction, sorry. Down. Go the other direction. Go further down in the. There, the AFNI would be this path, and then you can do AFNI. I think you need the entire thing. This is actually one line. It's weird that you don't have it because you.
I did this 3D copy, but I can't run the script.
It happened to me too when I tested it this morning.
Oh.
The paths are weird. It's annoying. I'm not sure what's happening.
Oh,
now
now
it
it
works.
works.
Okay.
Okay.
Okay, let's do the same thing with vaso and put it next to each other. So with vaso, we have kind of the same thing. The number of voxels is obviously the same because that's an inherent feature of the mask. The standard deviation is usually not as superficial biased like bold is, because a lot of these variants in the superficial layers in bold is coming from physiological noise of the large draining veins. Since vaso is not so sensitive to the large draining veins, we believe we don't have this huge variance up there, and it's more the variance down there. For the layer dependent activity, you see that we don't have this linear trend towards the superficial layers, but it's more an inverted U shape like this. Now let's deal with these zigzag patterns and get the number of layers more consistently. So for example, earlier I showed you on this example on the number of layers that if you choose too many layers, here like 100 layers, then we have them not connected. This is depends on the way how like on which kind of voxel grid we are working on. So for example, if you work in the original voxel space or if you work on a finer grid, so the layers that we drew were, where's my FSLView, obviously also works lives in the same voxel grid. So if we take those data, just upsample them to a finer voxel grid, we can get a more smooth borderline between gray matter, white matter, and CSF. In order to do that, we need to upsample the data, and I do this with AFNI. So if you look into your folder, you have a subfolder that's called scaled. So let's move into this scaled subfolder. In that subfolder, we have a script that I already prepared, the upsampling script, and then the same AFNI layer me again. There's no nifty there yet, so let's quickly copy the nifties to this one. I need to find my Google Docs again. Which one was this one? So now we moved into this scale space, and now we just copy the files that we just worked with into the same subfolder right there. So now we should have the same bold activation, the mean vaso, and the upsampled and the vaso act in that subfolder. When do we need to stop again?
4 o'clock, I think.
4 o'clock. We have 20 more minutes. Okay, we can do that. Okay, let's upsample it. I can show you what this upsampling thing does. It's as simple as it gets. It basically executes this 3D resample command and upsamples, like regrids the signal that we have on a finer spatial scale. So at the beginning here, I save the voxel resolution, I divide it by 3, and then I resample it to the new 3 times finer grid. And you can choose the interpolation how you like it. You can choose nearest neighbor, which some people say is the most conservative way of doing things, or cubic, which I like more. And we discussed this earlier a bit with respect to what Jonathan said yesterday, that my pen is here. Like if you I view the way how we acquire the data in k-space as not voxels, but data points on a rectangular grid. So we have a voxel centroid, and then we have a value of that voxel. I don't think we can assume that we have like rectangular cubes that have a certain value. Like k-space doesn't work that way. So in the sense that when we have a streamline like that, yesterday Jonathan said that this would correspond to a step function, that this has a certain value, this has a certain value, then this, and which results in this kind of pattern. But this inherently assumes that the signal intensity is homogeneous distributed in the voxel, which is not how the brain works, right? You don't have sharp edges of voxels. And I would think that we have like a signal value that kind of represents the overall weighted average within that voxel. So it's a strong assumption to assume that we have sharp borders of values. So I think that nearest neighbor is kind of a weird way of doing upsampling. And based on comments from Tim earlier, I might want to show you one thing. So there are maybe a similar like spin echo gradient, echo grace, and so there's no final perfect way on how to do things. It's like comparing bicycles with planes. I definitely, when I see do a linear interpolation or spline interpolation, the linear looks smoother. I don't want that. The spline looks noisier, and it might be because it amplifies noise, or it might be because it doesn't smooth data. Definitely, if you do a nearest neighbor or spline, it introduces weird shapes. So, for example, here you see that this circle kind of suddenly gets weird edges in there. So that's why I really don't like nearest neighbor. But yeah.
How about sync interpolation?
It looks very similar to the spline in my experience. So I think it's absolutely fine to do. Yeah.
So what's your recommendation?
I don't care. If your result depends on the way how you do your interpolation, I wouldn't trust the results. I use spline or a cubic.
From a theoretical argument, I suppose sync interpolation makes sense because it does credit to the k-spaceness of the data that
Right.
you've got. But I believe that in practice, sync interpolation is implemented as higher order spline interpolation anyway.
Right.
So,
Right. Yeah.
that's why they look
Right.
so similar.
Right.
So I suppose I agree with you. I don't care.
Right. Also, Valentin Kemper suggested to do it to upsample k-space and do it in k-space. Then there are even less assumptions with respect to the interpolation. So just in k-space, zero padded, and then do your FFT, which of course. Right. Right.
Because.
Right. A boxcar Fourier transform this sync. Right. Yeah. Right.
So zero padding is like sync interpolation?
Yeah.
Kind of, assuming that we have no phase in image. Like if.
I mean, it's a sync. I think. So I think the problem is basically what is finite in one, the support that is finite in one dimension and the other one. So I guess if you do the sync division really in image space, you would have a finite kernel size. Whereas if you do it in case space with zero filling, then you really have a finite rectangle in which you multiply the case space data, the rest is zero, which would be an infinite thing. Just decide where is your interpolation. So it must be very simple.
So we have 15 more minutes, so let's quickly go to the upsample space. This just upsamples it, so let's execute it.
Who's saying that we have only 15? Why?
Because, or was it?
Well, it was 4:30.
Oh, she said 4:30. Okay.
Okay.
We have time.
Okay. So upsample, we execute that command and give it the file that we want to have, which could be the Vaso act. That takes a while on the server, and I'm not really sure why. I think it loads it to some memory. Maybe that takes a while. Like on my machine, it's in a second.
Yeah, no, and also a bunch of us are also upsampling.
That's correct, yeah. Let's do this with all the files that we have. The Vaso act, the bold act. There's a weird warning. Let's ignore that. That's an AFNI problem, yeah. AFNI cannot deal with tilted slices. But since we are all in the same space, we don't care about that. And then the mean Vaso. Now we are in upsample space, so we need to also get layering in upsample space. So this might be a good exercise to just repeat what we did earlier. So again, I'm executing FSLView, mean Vaso, and then we can draw it again.
Can you take the old, if you already had the layer file from before?
You can.
Will it map onto this?
Depending on how you interpolate, I guess, because we had integers, and
or just the rim file?
I think like the point is here that we want to have the rim file more smooth.
Yeah.
So we upsample to have a better rim file.
If you want, if you just want to see it.
But you could nearest neighbor interpolate the rim file, and then you would have.
But you have to interpolate it first before you can view it.
Depends on the view. FSLView cannot deal with different grid sizes. FSLIs could. Yeah. Yeah. And your headers need to be right, which they are never when you work with in AFNI, or with tilted slices in AFNI. Yeah. Sorry, I'm not sure.
What was the header?
This is recorded, and I'm really grateful that the AFNI people help me a lot with everything I do. So there are some challenges with respect to tilted slices.
Yeah, oblique slices are really
yeah.
problem.
Yeah. Sorry, yeah.
Just ask Cheryl to be judicious.
So this takes a while because this is now an upsampled, the scaled mean Vaso. Again, I'm pressing Control 1 to get the single view because our screen is small enough already. I zoom in with the right mouse button. You can also zoom in with the magnification here. I'm not sure which slice is good, maybe 20. This is, I think, similar to what we had earlier. We have our calcrine. So let's draw it again. We need a mask, create mask, and then we draw our RI with the pencil. We have a fill value 1 and a size 1, and there's really an annoying delay here, so I do it very, very slowly. Earlier, Sean complained about the accuracy here, so I want to do it better now.
I didn't think it was topologically correct. Yes, okay, here's what you do. This is what I'm confused by. So you're not actually drawing a single surface, a single one.
You mean that I'm drawing two lines here?
But there's 2 lines rather than 1.
Right, and that's a serious issue, and I'm not sure if any program can deal with that. Like usually when you have, like let's say this is our x and this is our value, we have CSF, gray matter, white matter. Now in real life data, this is kind of smoothed out, so we have something like Fermi functions. Something like this. So this transition is smooth because our voxel is limited. Now, where do you want to draw your RIs? Usually, you want to draw your borderlines. That a voxel that's half filled with gray matter, white matter is the borderline, right? or same with CSF, that the voxel that determines the borderline or the position is at the border where it's half filled with gray matter, half filled with CSF. Now, in real life practice, it's not that simple, right? We have, for example, something like CSF, then we have something like, again, this is our position, we have something like gray matter, CSF, and then gray matter again and white matter. So no matter where you put your voxel here, CSF is too thin. You will never have a voxel that's half filled with CSF. So actually, for this side of the cortex, you would want your borderline that's half filled somewhere here. For this side of the cortex, it doesn't make sense, right? So I try to, like, you have always some curvature dependence on that. So I try to be as conservative as possible and just draw the borderline above gray matter, not at the, like, let's say if we have gray matter here, then this is smoothed out with a finite resolution. Then I would draw my borderline here where it goes to 0. And my gray matter for the layering is bigger than my actual gray matter, and then later I can cut it.
But if you imagine that you were flattening this, right? You've only drawn one half. So you're basically, so when you, right, you've not drawn a full CSF peel surface boundary here, right? You've just drawn one line and then extended it. So if you flattened it,
so the first layer that we have, like, this is not the layer, this is kind of the CSF layer. Yeah, this is outside gray matter. Yeah. So if you want to look at gray matter only, you cannot use the superficial one. This is the superficial and deepest layer, like layer 0 and layer max, is weird, which I didn't talk about here. Like here I usually treat them differently, the outermost ones. And like for the coordinate system in topography, if you like have them connected, you're screwed, right? Yeah. All right, you're right. Okay, we have more than 8 minutes left, probably. So let's quickly draw the gray matter white matter border here too. And since Alessio joined us, this is obviously the manual version of how you can do it. But you can also get those more elegantly with his ways of doing things. And in fact, I said that earlier too, so not just because you're here.
it's recorded.
It's recorded.
So again, we save it as rim.nifty. And because the paths are weird, again, I 3D copy it. 3D copy the rim.nifty to rim.nifty. All right, and now we can again calculate the layers. ln grow layers minus rim.nifty. Minus rim. And these are now many voxels. These are 1,000 times 1,000 times 100, a lot of voxels, so it takes a bit longer to do all this growing. And because it's a 3D thing, it really goes through every individual voxel in this entire matrix. And for most of them, it just fails to do anything because there's no borderline. And it does it twice for consistencies from white matter and for CSF. And it should be there in a second. And this is the Pythagoras error that I talked about, which kind of fixes these issues, if you remember. And I think it's not longer than 20 more seconds. Now we're done. So now we should have a file that's a layer.nifty file, which we can look at. Not this one. this happens when you load the wrong matrix size, John. Then it says it's incompatible. So the layer is what we want. And I think the file size is in the range of 250 megabytes or so. And it's just a single volume, right? So imagine if you have several thousand images in this upscale space. So if you do it on the scanner upsampling case space, then your data size is just, yeah, you need to be rich and have a lot of computing power. So these are our layers now. And now we can again extract this in upsample space and see how this looks differently. Again with the AFNI LAYNII, and now we can. Sorry, we need the scaled version. Scaled, bold. What? Where am I? This is a local script. Sorry. So now it looks much smoother. We have more homogeneous number of voxels per layers. In the second row, again, this is the variance of the signal within each layer. Within gray matter, it's kind of smooth. And then as soon as you have partial voluming with all the noise of the superficial layers or peel vessels or CSF pulsation, then it shoots up. In bold, as always, close to CSF, we have a lot of signal in the superficial layers. It's not a perfectly linear line here. And this kind of shoulder here, if you want to see it, might be what Alessio also sees as tree of Gennari. And now we can compare this with Veso.
What's the green line?
Sorry, the
green line.
The green line is the number of voxels per layer. So it tells us if we are rank deficient. What John, you were not here yesterday. So we have. Like if this goes up and down, you probably have too many layers and you have holes within your layers. Here we again see that we have more layers towards, like more voxels per layer in the deeper layers, and this is again due to the fact that we are concave in a sulcus. Like back there we have just more blue voxels than red voxels based on the geometry. If you have higher RI, this should even out. I don't really care much. Like at the end, you cannot really solve this problem anyway. This is maybe what Kendrick K refers to with its sampling bias. Right, this was the green one. And again, the same thing for bold, for Veso. Of course, the mask is the same, so the number of voxels is the same. The variance looks funny. This might be more representing the overall vascular density. So when you breathe in, breathe out, then all the vessels open up and they constrict at the same time. So we have a lot of vessels in the tree of Gennari. And also we have these peel arteries that are very vasoactive. I know that a lot of animal researchers kind of ignore that, including it's recorded anyway, and so the large vessels kind of contribute to, and you see that the overall magnitude in Veso has most of the activity somewhere where we would expect the tree of Gennari to be. We do not have this superficial bias over there. And if Cheryl gives me 1.5 more seconds, then I will.
I just want to let you know we're out of the scanner, and
okay.
We'll see you over in the break room when you guys are ready. So then let's
So the break room's ready for more.
just right through here.
So what, we
Count
need
on the
like
door.
10, 15 minutes or so?
Well, you want to have a
Can we
you
do
want-
10, 15 minutes?
You want to have a group discussion, right?
Yeah, Alessio needs to finish some slides from yesterday, and then we need a 15-minute wrap-up discussion.
Okay.
So
But I can squeeze it
you're
in.
only cutting into his time.
Right.
Don't work it out.
I can squeeze it, don't worry.
Yeah, we are almost done. Or yeah, or maybe if you give me 5 minutes, then we will do 2 more things. We will look at the scaled mean, like the anatomy, just as a reference, which is all like sometimes helpful. This is the kind of T1 weighted signal, where you see that T1 like is lower in the superficial layers. It's not a linear decrease, and this is particularly specific to the primary visual cortex, because there we have these kind of plateau, which sometimes becomes a dip, not always in the functional data. What I want to show you still is that you can do all kind of interesting things in this with these layers. For example, yesterday Jonathan said something about layer dependent smoothing. So let's play around with that with ln layer smooth. This program expects a layer file and an activity file that's smooth and a full width half maximum. So let's do some layer smoothing just for fun. Minus, maybe I copy this from up there. Sorry.
What units is full width half maximum?
Full width in millimeters. So your header should be not too bad, like should be in the right ballpark. Otherwise,
but it's an integer there, but it can be real.
You can do it 1.3 or something. Activity map. So let's use the scaled Vaso one. The layers is called layers, and I hope this runs fast. There are 20 layers, yeah.
Not considering this also.
Right, you can have the sulk touch option, which might again be referring to what you did, what you mentioned, that when you have kissing gyri, like that, it can happen that when you smooth this layer, you smooth within the layer, right? But here there's a layer that's also not too far. So depending on, like not with 1 millimeter, but if you do more, then signal can leak here to here. If you do the non-sulcus touch thing, then it only considers neighboring layers to do the smoothing, like Anna Blasevskaya does in FreeSurfer in vertex space. This is all in voxel space, because then you don't need to resample images again and again. So now we smooth the Vaso, and we can again look at that before and after smoothing. And now I'm just showing you one example, like ln. There are many different things that you can play around with, and yeah. Now we just did the smoothing, so let's look at the Vaso activity map, scale Vaso act, and the automatic scaling here is kind of weird, so we need to scale it. So I think from 2 to 4 we did earlier, right? 4 is maybe too much. 2 to 6. Let's make it yellow. So here you see the activity of the tree of Gennari. It's kind of bumpy and weird. If you want to see it, and I looked at noisy data a lot of high percentage of my life, I see a line there. If you don't see it, let's look at the smoothed one, which would be the smoothed one here.
So this looks already smooth, but apparently in an isotropic manner.
Well,
this is the
upsample.
upsample.
It's the upsampled, so interpolated, right?
2 to 6.
It's not on the original grid.
Like earlier we looked at the original grid with 0.5, and this is now 3 times higher, so this is 0.8 to 0.18. That's why it looks smooth. So this is the difference with. So wait, the delay is pretty annoying. So this is the original one, and this is the smooth one. But as Jonathan said yesterday, you cannot use that to as an to identify if you have layer activity, like it's circular, right? You smooth it to see layer stripes, so you cannot use that to say, hey, we have layer stripes. Yeah.
But if you had a separate independent sample, you could.
Right. Right. And I think.
So wait, what do you do with the independent sample?
No,
it's not a model, right? I mean,
no. If you had like two, odd even
right.
runs
Yes.
from the same subject.
Yes, absolutely. Yeah. Good.
Okay. Are there any questions about that?
The Slack channel will be busy.
Yeah. Yeah. Also, like if you have trouble trying this at home, I said this. Did I say this in this session? Like there is a YouTube tutorial on how to do this thing. There's a, where is it now? Sorry. There's a YouTube tutorial. There's there's the blog post on how to do this thing. You can't go through these things before you ask questions, and right. But I'm always happy to. Yeah. Right. Do you have a question? No. Okay. Thank you very much.
Thank you.